Chapter 4, Part 6, Conformations of Cycloalkanes. So, cycloalkanes have an interesting factor that we don't have to worry about with non-cyclic alkanes, and that's that they have this thing called ring strain. So, ring strain comprises of two things, angle strain, which is a result of the deviation from your ideal bond angles caused by the structural constraints of being a ring. So if you remember, an sp3 carbon atom likes to have bond angles of 109.5. But if you're forcing several carbons to form a ring, those angles between the carbons are going to be either quite a bit smaller or possibly larger than 109.5. And so that causes strain within the ring. There's also torsional strain, which is the result of the dispersion forces that are being forced due to the restriction of mobility caused by being closed up into a ring. So let's take a look at cyclopropane. Cyclopropane has bond angles here that are far from the preferable 109.5 degrees. Because of this, cyclopropane is not very stable. The internal bond angle within cyclopropane is 60 degrees, which is a little more than half of what it should be. So it's about 50 degrees deviated from the ideal tetrahedral angle. So there's a lot of ring strain on cyclopropane. And in fact, if you take an organic modeling kit, it's actually really difficult to make a model of cyclopropane because the plastic pieces that you're using are meant to be 109.5 degrees. And so I've actually broken several models trying to demonstrate cyclopropane. There's also some really unfortunate torsional strain caused by the fact that all of the carbon atoms within cyclopropane are coplanar, which also means that all of these atoms are eclipsing each other. So if you were to look down one of these bond angles and create a Newman projection, you would see that these two hydrogens are overlapping and the bonds to the other carbon overlap. And so this is constantly being forced into this eclipsed conformation. Cyclobutane is only slightly better. The addition of another carbon atom allows it to do this little pop out of the plane. So instead of having like a perfect square, two of the carbon atoms kind of pop upwards and the other two kind of pop down. And so this allows it to relieve a bit of ring strain and definitely a lot of the torsional strain, because if you were to look down this bond, you would no longer see the hydrogens eclipsed. This hydrogen would actually be just kind of next to the other one. The bond angle there is about 88 degrees, which is still quite a bit off of the preferred 109.5. And then the cyclobutane is also not planar, it's slightly folded. If the cyclobutane ring were planar, the angle strain would be less because the internal angles would be 90 degrees instead of 88. But all of those hydrogen atoms would be eclipsing each other just like they were in the cyclopropane. So this molecule actually has those carbon atoms popped out, and the bond angle is a little smaller because it allows the molecule to relieve a lot of that torsional strain from the overlap. Now, cyclopentane is really cool. It has this form called like an envelope form. So most of the carbon atoms are more or less planar with each other, but by popping one of the carbon atoms out of plane, it allows enough rotation around these bonds that you don't have direct overlap between all those hydrogens. So that's what we're seeing here with that carbon kind of popped out. If cyclopentane were planar, the bond angle would be 108 degrees, which is really close to the normal tetrahedral angle. But it would still have all 10 carbon-hydrogen bonds eclipsed, which is problematic.